The first big problem in calculus was rates of change or derivatives. The second big problem of calculus is areas. So we're talking about just an area of a shape in the traditional sense, which you know how to do, but now we're talking about the area of specifically curved shapes. So you know that the area of a circle is pi r squared. That's the one you know. You've never really seen proof of that fact because you actually need calculus to prove that fact. So we're gonna do that in Calc 2. But just think of any shape that curves, like a circle or an ellipse or like a lake, like a landmass, anything like that, or just any kind of blobby curved shape. And then you can extend that to 3 dimensions. Think about like finding the volume of something that curves. So like a vase type of shape, or like the volume of a loaf of bread. How would you do that with math? There's no real formula from geometry for it. So we got to go beyond geometry and, well, we have to use calculus. We'll just start with an example. So picture the parabola x squared from x equals 0 to x equals 1. You don't have to picture it, I'll show you. And we're going to find the area under the curve, and we're going to use that phrase a lot, so I'll explain it. So by under the curve, it's under the curve and above the x-axis. So bounded by the curve and the x-axis, and in this case between, okay, the origin, x equals 0, and then x equals 1. So that little shape, it looks like a right triangle, except that the hypotenuse of the triangle is curved. That's what we're going to find the area of right now. Whatever that area is, we're going to call it A just to give it a name, and then think about it. A is less than 1/2. Why? Because if that were just a right triangle, if it were just half of that square, then the area would be exactly 1/2, right? Because the area of the square is 1. But it's a little less because that isn't a triangle, because the shape curves in a bit. So whatever it is, right, agree with me that it's slightly less than 1/2. Here's the setup. We're going to take that region pictured, and we're going to chop it up into 4 vertical strips. And they're all going to have the same width. So if you look at it, the whole interval is 1, so each of our 4 strips is going to have width 1/4. I know this doesn't seem like calculus, and it seems like we haven't done anything like this. It is calculus. You'll see it. The number 4 isn't special. We're just starting with 4 because it's easy to picture. So we're going to take our 4 vertical strips that all have width 1/4, and we're just going to draw a rectangle over the top of each one of those strips. All right, so now we have these 4 rectangles. Now, we know how to find the area of a rectangle. In fact, it's quite easy. It's just width times height. So if you look at the area of all 4 of those rectangles combined, the sum of the areas of the rectangles, it's bigger than the area of our shape. So it's not good. So this is a bad approximation, but we're going to make it better. So we're going to take our strips, we're going to draw rectangles on top of them, we're going to find the area of those rectangles. They all have the same width, 1/4. The height of every rectangle is just the value of the function at wherever the right endpoint of our little subintervals are. So if you look at that first small rectangle, the height of that thing is 0.25 squared because it's specifically x squared. The height of the second rectangle is 0.5 squared, right? Because that's where we drew it. That's where the curve is. The height of the third rectangle is 0.75 squared. And the height of the fourth rectangle is just 1 squared, or 1. So that last rectangle, the biggest one, the area of that thing is just 1/4, because it's 1 high and 1/4 wide. All right? So the width is determined by how we chopped it up. The height is determined by whatever function we're dealing with. Those are our 4 heights, and now we can very easily compute the areas of all 4 rectangles and just add them together. The rec. Let's give this a name too. So the total area of all our 4 rectangles added up, we're going to call R4 because there's 4 of them, and we're using the right endpoint to draw the rectangle. We'll use the left one in a second. So let's compute it. That's just calculator stuff. So look at what you're doing now. It's just width times height plus width times height plus width times height plus width times height. And I'm writing like 2/4 and 4/4. I know that's goofy looking, but I'm writing that for a reason. The number 4 isn't special. We could have chopped this interval into 17 little strips. And then it would be like, okay, 1/17, 2/17, 3/17, 4/17. So that's why I'm keeping the fractions like that, because obviously we want to make this more general and see how we do this for everything. You can always factor the width out front because remember the widths are equal. That's really the only stipulation. We can draw the rectangles actually however we want, but having the widths be equal is important. So you can take that up front and then you're just adding the 4 heights. And that's just calculator stuff. There's no reason to do that by hand. That turns out to be about 0.46875. So that's an approximation, and it's a terrible one, right? There's way more area in those rectangles than there is under the curve because there's all that stuff that hangs over it on the top. So all that's extraneous, and it shouldn't be there. So this number's too big, right? The way we've set this up, this is obviously an overestimate for the area we actually want. So we already kind of knew what A should be, but now we know that it's less than 0.46875, right? Because these rectangles are too big. Do the exact same thing again, except now we're going to use the left endpoints to draw our triangles. So if you look at that biggest rectangles, if you look at that biggest rectangle, the height of that thing now is 0.75 squared. So now our rectangles sit inside the curve instead of like overlaying the curve. And if you look at the smallest rectangle, it's not even there because the height is 0. So I'm still going to call it a rectangle. It's just a rectangle with height 0 because we use the left endpoint to determine the height, and the left endpoint of the curve is 0. So we're still going to include it even though it has no height. It's just obviously not really going to do anything. So just think about it again. We're going to add the heights, add the areas of 4 rectangles, and we're going to get an underestimate for this area, right? This is too small. This is much too small, but do it anyways. Same deal. We can bring the width out front because the widths are all still the same, and then it's just the sum of all the heights. So it's 0 squared plus 1/4 squared plus 2/4 squared plus 3/4 squared. So those are the 3 rectangles you actually see. Those are the heights of them. 1/4 squared, 2/4 squared, 3/4 squared. And just mash that into your calculator. You get that, 0.21875. So that's not a good estimate either. There's a ton of area that's unaccounted for now, right? There's a ton more area under the curve than there is in the rectangles. But now we've refined it. Now we're not just saying, okay, A is less than a half. We know that A is somewhere between 0.21875 and 0.46875. And now we make it better. So the next step should remind you of a limit. And it should kind of start to remind you more of calculus. Now we do the same exact thing, only we're going to use 8 rectangles. And again, the number 8 isn't special either. We could just as easily do 10 rectangles. But just agree with me that this is better. This is a better estimate for the curve because it's closer to the actual area of the shape. And if we were to use 16 rectangles, just picture twice as many rectangles in there, it would be even better. If we were to use 32 rectangles, 64 rectangles, 1,000 rectangles, it would be a pain, but it would be closer. So the more rectangles we use, the skinnier our rectangles get, and that gets us closer to the actual area of that curved shape. And that's the part that should remind you of a limit. That should remind you of calculus. Because even if we used 1,000,000 rectangles, we wouldn't quite be there. But if we look at the limit of what happens as the number of our rectangles goes to infinity, then that gets us the exact area. So the exact area is a limit. And you can either think of it as the number of rectangles going to infinity or the width of the rectangles going to 0, right? You can't actually have infinitesimally skinny rectangles, but we can talk about a limit because we know how to do that. So again, this is just number crunching. The width of these ones are all 1/8, and the heights are just the value of the function at every eighth. So 1/8 squared, 2/8 squared. So that's our expression for the sum of the areas of these 8 rectangles, which turns out to be about 0.3984375. So we're getting closer. That's the idea. We're not going to do this all day. We're just going to say the more rectangles we use, the better this gets. So there you go. I've done the work, or a computer has. So the first row is when we use 4 rectangles, that's our underestimate and our overestimate with left endpoints and right endpoints. So drawing the rectangles too small or drawing them too big. If we were to use 10, you'd get those numbers. If we were to use 20, right, 50, 100. So look at the 1,000. Using the left endpoints, we get that 0.33283 number. That's still too small. Using the right endpoints and 1,000 rectangles, we get that 0.33383 number. That's still too big. But we know that the real area is between those two numbers. And if you look at those two columns going down, right, they're converging. They're converging together. And when they eventually did converge together, we would have our exact area. Now, they never actually will, right? We could use 1,000,000 rectangles and it'd still be a little off. But if you think about what's happening to those two things as n goes to infinity, that limit that we never actually reach is the exact area. And if I tell you that it's a nice even number, you can kind of guess that, oh, maybe it's 0.333333. And if we just kept going, we'd fill in more 3s, and that's exactly right. So it's 0.3 repeating. Spoiler alert, this area is exactly 1/3. And we can do this with math. We're not going to do this with rectangles. The rectangles give us the basis for the math that we're going to use in the future. We just have a lot of work to do before I can really tell you how to do that. It's actually not pretty easy. So it's a limit, and both of those columns are converging to the same number. You'll just have to take my word for it. Your book has a way of doing this with algebra. We're just going to do it with calculus. And I'll just telling you that they're both converging to exactly 1/3, which is the exact area. We don't have to use endpoints to draw our rectangles. If you look at the way that's pictured, we're using the middle of the interval. So in each of our rectangles, we get a little area that's over, but we also get some area that's under. So they kind of compensate for each other, right? If you look at that third rectangle, it looks almost exactly right because there's about as much green stuff as there is white stuff. So those kind of cancel each other out. So using what we call the midpoint rule is a better way of doing this. If you had to compute this by hand, which you do at some point, this is a thing. It's called a Riemann sum. But it's boring to do by hand, and it's still just more number crunching. You don't even have to use rectangles. You can use trapezoids where it kind of follows the curve a little more. It actually turns out that the midpoint rule is even better than the trapezoid rule, so I'm not even going to introduce it. The important thing is no matter how you draw them, if you use enough rectangles, if you use 1,000 rectangles, 10,000, whatever, that sum, the sum of the areas of all your rectangles is going to converge exactly the same way. It doesn't matter how badly or well you draw them. So it'll always converge to the same number if you take enough of them and if you just let n go to infinity. This seems like a completely different thing out of left field again, but it's actually kind of the same problem. And it gets us a little bit more into calculus type stuff that we're familiar with. So this should kind of remind you of the very first stuff we did, rates of change, except going the other way. So here's the scenario. It's not realistic. Your car's odometer is broken, but your speedometer works fine. So you know exactly how fast you're going at all times, but you don't know how far you went, right? It makes sense that you should be able to get there. If you know how fast, right, your speed's always varying, but if you know how fast you were always going, you should be able to figure out how far you traveled, and you can. So again, unrealistic, don't do this, focus on the road, right? But suppose you just glance at your speedometer at every 5 seconds for like 30 seconds here, right? So you did it and you made a note of your speed, and then you did it 5 seconds later, noted your speed. So you sped up from 17 miles an hour, 21 miles an hour, 24, etc., all the way up to 32, and then 31 miles an hour. And you want to use those numbers to figure out exactly how far you traveled over the course of that 30 seconds. The first move is, since our time is in seconds, our speeds have to be in seconds too, so we can work with them. So your car obviously does miles per hour. We're going to convert them to feet per second. So you're doing a lot of mental math here while you're driving, which I would not advise. So that's just unit conversion, converting those speeds to feet per second. To 17 miles an hour is 25 feet per second, 21 is 31, etc. So you started off going 25 feet per second, and then you went up to 31. Now, obviously, there's numbers in between there, and you should kind of think, oh, what if I did this same exact process every 1 second? Wouldn't I get a better picture of how far I traveled? Yes. We're not going to do that because it involves a lot of calculating, but the more speeds you use, the better your approximation is. See what I'm saying? It's a limit. So we're making a big assumption here, and it's a bad assumption, that our speed just suddenly jumped up from 25 feet per second to 31 feet per second. It didn't. It's continuous. It's a continuous phenomenon. It hit all the numbers in between there during that 5-second period. But we're just approximating, and we're just doing this on paper. So we're going to use our numbers here to say, okay, the distance is rate times time. So the distance we traveled in that first 5 seconds is 5 seconds times 25 feet per second, right? 5 seconds times 25 feet every second is going to be 25 times 5, which is 125. So we're saying in that first 5-second interval, we went 125 feet. So now it's just number crunching again. So notice all the times are the same. The time is always 5 seconds. So that should remind you of our equally wide subintervals. We chopped it up into 5-second time increments. So all the times are the same. And then the rates changed. So you could factor that 5 out front. So it would just be 5 times, what, 25 plus 31 plus 35 plus 43 plus 47 plus 46. So that's what it turns into, just calculator, that's 1,135 feet. So that's our estimate. Again, it's not a great estimate, but it's the best we got. So that's how we can get distance traveled from a speed. And more generally, we want to get the total amount that something has changed, that's called the net change, from a rate of change, which again should remind you of doing a derivative. It's the same kind of thing. Here's our speeds at all of our 5-second intervals. That's what those dots are. Now again, just imagine if there was way more dots. So if we were some sort of a robot and we did the time intervals every 1 second, right? You would get a better graph. You'd get a better number. Your time intervals would now be 1, so you'd be doing 1 times your first speed plus 1 times your second speed, on and on and on, and then I guess we'd actually have like 29 speeds in here. So the exact distance traveled, we're never going to figure it out, even if we look at it 1 millisecond at a time, but it is a limit, right? The more we do, the better this gets. And visually, just picture there being 6 rectangles on this graph. That's an area, right? It's width times height. The width is 5 seconds, the height is the rate. So this is the exact same problem as the last problem. If we had to visualize it, we're just adding the areas of 6 rectangles together. And if we had 600 rectangles in here, it would be better. And so the total distance, the thing we're trying to find, is actually the exact same thing as the area under a curve. So area under a curve is not just a geometry problem. It's cool to be able to find areas of curvy shapes. It's a thing we're going to be doing a lot, but it's not just geometry. It has a practical use as far as working backwards from a rate of change to figure out the net change. Picture a curve connecting those 6 dots. That's your actual velocity, right? It doesn't jump, it curves nicely. It's a continuous, speed is a continuous phenomenon. Your car can't jump speeds. And if you picture that curve, the thing that we're trying to find all along is the same exact thing as the area under a curve. So if you have a rate of change, and we'll make this more clear later, the total amount of change, in this case is distance traveled, is visually the same exact thing as the area under your speed curve. So we're kind of spoilering where we're headed. The rate of change is the derivative of like distance traveled. So if we're trying to figure that out going the other way, that's a derivative, only we have to go the other way.